G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening. Or I pray that God is blessing you if you're facing a few challenges. Just move my picture down. This is lecture one, and this is part B. We're only going to go through one thing, which is bounded and unbounded sets. It will take a little bit, and then we'll get on to part C. So let's get into it. Okay, a set is a collection of clearly defined elements. In set notation, we only use curly brackets, or we don't only use, we use curly brackets and commas. Now, you should have seen this in high school. So A equals 2, 4, 6, 8, or something similar to that to say that is a set. Now, in high school, you might have used round brackets or square brackets or whatever, and it really didn't matter. Here it sort of matters, so we'll keep to definitions. Okay, now if you've done any previous subjects with me, you've probably seen this type of thing, and you might have seen that on the internet as well. So I've just given an explanation of this. So T, let's move my image down a little bit further. T is a set for all x, so this upside down A for all x, which is an element of n, the natural numbers. And you've got this, I've highlighted such that for a reason here. You've got this colon such that there exists is the backwards e, and n, which is an element of the natural numbers for which x is twice n. So that's what that's saying. And the reason I've highlighted the such that is because often you'll see in textbooks or on the internet the colon and the line, and they're meaning the same thing. It's still meaning such that. So here's the start of it, then they say such that, and this is some condition. Okay, so if I use a colon or a line, it's just interchangeable. Here's some simple examples. X such that, so the set of all numbers x such that they are 3 less than a natural number. So that's a way of saying what that is. So the set of all numbers such that they're 3 less than a natural number, and if you had to express that, minus 3, minus 2, minus 1, 0, 1, 2, etc., etc. And what I've done here is put virtually the same thing. So you've got x is an element of n such that, and I've just written the colon and the line interchangeably, but the only thing I've changed is that. And it looks like I've said the same thing. It looks like if you look at that and you look at that, haven't you said the same thing, sir? No, I have not. And hopefully you can pick up the difference to say, okay, if you had to list this set versus listing this set, you'd actually be able to discern the difference. So let's see what it is. It's a set of all natural numbers such that they're 3 less than a natural number. That bit's the same. But if they're already in the set of natural numbers, they can only start from 0. So they can't actually start from minus 3 because I've defined this part of it to say x must be an element of the naturals. Here you've just got x is anything. Okay, so just be careful of what is defined on different parts because it can mean a different answer. Stay alert. And note that I've just used that and that interchangeably. So that's just for awareness as well. But certainly be aware of what's going on. Number types now, you would have seen this in high school for sure. N is the naturals, Z is integers, R is reals, Q is irrationals, I is irrationals, C is complex, and M is imaginary. So I've given an example there, 3 plus 2i. Complex is just the I, so minus I, plus I, 15i, etc., whatever the complex value is. The imaginary is adding some sort of real part to it. Okay, sets and a power set. So now I've sort of covered the basics of what you should have seen. This is things you probably haven't seen. So a power set. A power set is a set which includes all the subsets, including the empty set and the original set itself, and is usually denoted by P and round brackets. So let's give an example. T is X, Y, Z. So there's a set. Well, the power set is going to include all of the combined the combinations of X, Y, and Z, as well as X, Y, Z, and the empty set. So the power set of T is X, Y, Z, X, Y, X, Z, Y, Z, and X, Y, Z, and the empty set. So that's the power set. If a set contains n elements, a power set will always contain 2 to the n elements. So how many is in this? 3. 1, 2, 3. So T's got 3 elements. And how many is in this one? 1, 2, 3, 4, 5, 6, 7, 8. So PT has 2 cubed elements, which is 8. There you go. So it doesn't matter what this will be, the power set will always be 2 to the n. So that's the cardinality. The number of elements in a set is the cardinality. That's written as an absolute value. So the cardinality of T is absolute T is 3. The cardinality of the power set is, image in the way there. Cardinality of the power set is absolute PT, which is 2 cubed, which is 8. So fairly straightforward concepts there for you to remember. Just remember the word cardinality and 2 cubed. And make sure you include that empty set. Okay, bounded and unbounded sets. Right, move the image down again. Okay, a set of real numbers is bounded if it has both an upper and lower bound. So you can consider bounds pretty much the same as limits, if what you did limits in high school. An upper bound is a number that is greater than or equal to. Now pay attention there. It's greater than or equal to, not just, it's the limit, the final number. It's greater than or equal to all elements of the set, while the lower bound is less than or equal to, again, less than or equal to all elements. An unbounded set has no upper or lower bound. Well, that's pretty obvious. You don't need to be Sherlock Holmes to figure that one out, do you? Okay, so trying to put a bit of humor in there. Okay, Q is unbounded, so it just goes, the dot 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 means it just goes on forever to negative infinity, and this dot 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 means it goes on forever to positive infinity. That's pretty easy. N is bounded, so the counting numbers 0, 1, 2, 3, and etc., etc. It's bounded below by 0, but not above. Just a note here, I've included 0 in the counting numbers. Again, you can do your own research into maths to think, well, I should include just 1 or I should start from 0, and there's arguments either way. It's important actually to include the 0 when you're doing multiplication. If you want to stay with the same number, you've got to multiply by 1. But if you want to do addition to stay with the same number, you've got to use 0. So I think it's important to include that 0, but there's arguments both ways in terms of counting numbers for the naturals. I'm including it, so just so you know. Okay, 3, 0, 1, 0, 1, and 2, 100 are bounded. Hopefully you can remember the difference between round brackets and square brackets. Can you? If you can't, that's okay. I've written it out down the bottom. So round brackets, open interval, not including the endpoints, so it doesn't include the 0 or 1, it does not. And closed brackets, closed interval, includes the endpoint, so this includes 0 and includes 1. How was your brain there in that little quiz? Okay, for cos x, where you've got x is an element of the real, is bounded, since we all know that cos x exists in between -1 and 1, and there's a little graph just showing that. And all finite subsets of R are bounded, of the reals are bounded, and some infinite subsets are. So this is a bit of a strange sentence, but let's just think about that so you can keep that in your head. What's actually happening? So let's make it an infinite subset. Well, reals go from -infinity to infinity. Right? How can you have an infinite subset? Well, let's think about that. Let's go from the numbers 1 to 2. You think, well, that can't be an infinite subset. There's only like 1 and then the numbers in between and then 2. That's a finite subset. No, well, no, it's not. It's infinite. So if I tell you I want every single decimal between 1 and 2, what are you going to do? You start with, let's go 1.1, 1.2, 1.3. Well, I want every single decimal. So I want 1.01 plus 1.001, 1.0001, and every single decimal. So now you've got to go, the first number after 1 is 1.00000, and you go off infinitely before you even get to the next number. So there's an infinite number of numbers with a decimal between 1 and 2, which is quite strange that now you've got infinity within infinity. And if you want to keep dwelling on that, you'll start dwelling on what Einstein did. So But there you go. There's an infinite subset within the reals, which are an infinite set. So don't spend too long on that, or your brain will be going, "Oh, hang on, I'll lose the plot." Okay, so there's an infinite subset example. Okay, so here's some questions. Get my image down the bottom again. There we go. So, are the following sequences bounded? So I've just listed A and B and C, and for the A, B, and C, not for any particular reason. And you've got A and n 0 to infinity, 0 to infinity, and 1 to 30. And this is how we're defining it. So an is minus 1 to the n cubed. Bn is 2 to the minus n, and Cn is n squared. So they're the ones we're going to, are they bounded or not bounded? So let's look at them one at a time. So this is unbounded. And how do we know that? So there's no m such that for n greater than 0, we can have that. That's just not going to exist. How are you going to look at that in a test or an assessment is literally by trial and error. Start with n equals 0 and then do n is an infinity. Now, you can't press n infinity into your calculator. That's not possible. However, you can press 0. So if we put in 0, we get the 0 in there. Minus 1 to the 0 is just 1. 0 to the 0 is 0. So 0 cubed is 0. So 0 times 1 is just 0. Put in 1, and we get minus 1 times 1 is minus 1. Put in 2, and we get 8. Right? Minus 1 squared is 1, and then 2 cubed is 8. So you can see it's starting to oscillate between negative and positive. Do it again. It will just keep oscillating backwards and forwards in negatives and positive. If we get it n large even, so if you're doing it in a test in your calculator, you might press in, 100 or 1,000 or something. So put, minus 1 to the 1,000 times 1,000 cubed and see what happens there. N is large. If it's even, it's going to be a very large even positive. And if you add plus 1, it's going to be a very large odd negative. So you can see this massive oscillation here. It's just going to keep going forever and ever in both directions. And that's how I would try to do it in an assessment. You would just use your calculator, put in a few numbers and go, yeah, no, that's definitely going to be unbounded. Second one, sequence, again, using your calculator. This is going to be bounded. So putting in 0, you obviously can put in any limit that they put in there or any bounds they put in there to start with, which isn't infinity. And for infinity, like I've just explained, just put in a big number in your calculator and just keep adding on to it and you'll see where it's going. So put in 0. If we put in 0 there, 2 to the 0, anything to the 0 is 1. So that's an upper bound. Because this is negative, it's going to get smaller and smaller. Put in 1. 2 to the minus 1 is just 1 over 2. Put in 2. 2 to the minus 2 is a quarter. 2 to the minus 3 is an eighth. And you can see this is just going to get smaller and smaller. And n is very large. It's going to be very small, approaching 0, which is our lower bound. Let's do another one, or the third one, n squared. So put in 1, we get 1. There's our lower bound. Put in 30, that's 900. That's our upper bound, and that's it. Pretty easy. So that is definitely bounded, and a very easy one to put in your calculator and find the answer. The supremum is the least upper bound of a set. Now, that's a really interesting statement in the way they say it's the least upper bound of a set, while the infimum is the greatest lower bound. Again, greatest lower bound. Interesting. So let's have a look at that. Find the supremum and infimum of the set. 3 squared minus 10x plus 3 is less than 0. So this is just a quadratic. Factorize the quadratic, 3x minus 1, x minus 3, which you can do because you're talented people. The supremum is therefore 3, and the infimum is therefore 1/3. Now, if you're thinking a little bit, you're thinking, hang on, you've got upper bound, lower bound, and then you've got an infimum is the greatest lower bound, the supremum is the least upper bound. What the heck is that? And hopefully you've thought that and thought, So here I'll explain what is the difference between supremum and the upper bound. Have you figured it out? No? Well, that's good because I'm going to explain it. Okay, so let's consider S is X is an element of Q, the rationals, and we're going to go 0, X is less than or equal to root 2. So an upper bound is 2. An upper bound is also root 2. Okay, so you've got root 2 and 2 there. I should actually have this as I as the irrational, shouldn't I? So an upper bound is 2. An upper bound is also root 2. So they're both upper bounds. And you think, well, how is that possible? Well, what's the definition of an upper bound? It's just got to be greater than or equal to the maximum. Well, the maximum thing you can get inside here is root 2. There is no greater maximum. But this is greater than root 2, so I can say that's an upper bound. The supremum is only root 2, so we can say that there exists a supremum, which is root 2. The lower bound is 0, because it's obviously there. It can't get below 0 because it's got to be greater than 0, so I can say a lower bound is 0. Now, I didn't ask that in this question. I just thought I'll just add this in. Well, then if you've got this lower bound, what's the infimum? Well, there is no infimum. You can't get a number greater than 0 so close to 0 that you can figure it out. So we can say there's no infimum, so we can say there exists with a line through it, there does not exist an infimum for X. Okay, that's it for the moment. I'll see you in part C. God bless you, stay safe, and keep studying. Okay, bye.